In this part, we are going to discuss about tray stability diagram or performance diagram, or in somewhere it is also written as tray operating diagram. And we are also going to discuss about dumping in detail, because in part 1 we have just introduced about the concept of dumping. We hadn't gone in detail, so we are going to cover dumping in detail in this part. And we are also going to discuss about mechanical problem which may lead to flooding and weeping in a column. And we will conclude our this part by defining turn-down ratio. So let us start our lecture. Now we have discussed about weeping and different types of flooding mechanism, and we have also discussed about what are the factors which affect this flooding or weeping. So if I summarize all these factors which I have already discussed, then I will get this diagram. And in this diagram, on x-axis this is liquid flow rate, and on y-axis it is vapor flow rate. And here you can see that this diagram shows that for a satisfactory operation there will be a limit of vapor flow rate and liquid flow rate. For example, when liquid flow rate goes high, then we have discussed that it may lead to downcomer backup flooding, and if my downcomer entrance area is less, then at high liquid flow rate downcomer choke flooding may take place. And because of that reason, there is a limit of high flow rate. Before this limit, if your liquid flow beyond this limit, if my liquid flow rate goes high, then this may lead to flooding. Similarly, there will be a limit of high vapor flow rate. For example, at low liquid load rate, flow regime usually remains in a spray regime, and in that case, if my vapor flow rate goes high, then it may leads to a spray entrainment flooding. Usually at high vapor flow rate, entrainment rate increases, and in the case of excessive entrainment, it may lead to a spray entrainment flooding. And because of that reason, somewhere in other sources like in Cedar and Hanley, here instead of writing spray entrainment, it is written as excessive entrainment. Okay. Similarly, when my liquid flow rate is moderate, and in that case vapor flow rate goes high, then it may lead to entrainment or jet flooding. It may lead to either spray entrainment flooding or froth entrainment flooding. Any of one of them could take place. For example, if tray spacing is small, then it may lead to froth entrainment flooding. But if tray spacing is high, in that case it may lead to spray entrainment flooding. So there is a limit of high vapor velocity. Similarly, when vapor velocity goes low, then we have already discussed that it may lead to weeping. Okay. Now here we can see that this weeping curve is like this, because when liquid flow rate goes high, then chances of weeping goes high, because in that case hydraulic tray pressure drop becomes high, and usually weeping take place when dry tray pressure drop becomes low compared to hydraulic tray pressure drop. And because of that reason, if my liquid flow rate is this and my vapor flow rate is this, then I am in safe region. I am in a stable operation is there, efficient operation is there. But for same vapor velocity, if liquid flow rate goes high, in that case it will goes into this excessive weeping region, because when liquid flow rate goes high, then the dry pressure drop required to hold the liquid on the tray also becomes high, and because of that, higher vapor flow rate is required to avoid this weeping. So this is okay. Now here is another point that is called dump point. Below this vapor flow rate, liquid will start dumping through the tray. None of the liquid is flowing over the weir, and all of the liquid is flowing to below tray through the sieves only, and this is called dumping. And now we are going to discuss about dumping in little bit detail. So we have to discuss 2 points. One point is dumping, how dumping reduce tray efficiency at very low level, and why this curve is not like this weeping point curve. This curve is like this. That means when liquid flow rate goes high, then dumping chances of dumping goes low. So these two things we have to discuss. So let us discuss about first how tray efficiency goes very low when dumping take place. Okay, see, whenever weeping take place, then tray efficiency goes low, but it do not reduce tray efficiency at very low level. Why? Because even if liquid is flowing through the sieves, then also there will be a chances of vapor and liquid contact, though it won't be very intimate contact, but there will be a chances of liquid and vapor contact. So there will be a reduction of efficiency, but not at very low level. But what happened below dump point, tray efficiency reduces to very small fraction of normal value because mass transfer goes very low. Why it is so? Because when dumping take place, no liquid entering into the downcomer, and when no liquid entering into the downcomer, then what happened? Downcomer loses its liquid seal, and because of that, vapor goes through the downcomer. And because of that reason, many times it is written as dump point as seal point. Okay, so some places dump point is also represented by seal point. So let us explain this point, what it is saying. So suppose normally what happened? Vapor on a tray flows from below tray to above tray, and it goes in vertical direction. Now question come, why vapor flows in this way only? Why can't it flows through this downcomer clearance inside the downcomer? And the reason is there will be always a liquid flowing through this downcomer, and because of downcomer clearance, and because of that reason there will be a sealing by liquid which restrict vapor flow inside this downcomer. So liquid provide a seal of downcomer clearance for vapor flow. Okay, now what happens when dumping started? Now when dumping started, then what happened? All of the liquid start dumping through this sieve holes, and none of the liquid is flowing inside the through the downcomer. Then what happened? This downcomer clearance, it becomes unsealed because there will be a very less liquid level. So what happened when downcomer seal lost on, let's suppose, tray deck 1, then what happened? Vapor will start flowing through this way. Now when vapor will start flowing through this way, it will do? It will restrict liquid flowing from tray 2 to tray 1. Okay, so why? Because the vapor which is flowing from the tray 1 having higher pressure, and if higher pressure vapor goes this way, then liquid will not be able to drop through this downcomer, and because of that reason liquid will back up on this tray, and because of that reason what will happen? Two things will happen. One thing will happen that most of the vapor is flowing through this downcomer, so very less vapor will flowing through this tray spacing, and because of that reason dry tray pressure drop for this tray will go low. Similarly, because of this liquid backup on this tray, hydraulic tray pressure drop goes high, and what it will lead? It will lead weeping on this tray 1 also. Okay, so in this case what we find that when dumping started, what happened? There a huge channeling started, because most of the vapor start flowing through this downcomer, and most of the liquid start flowing through this tray spacing, I mean the active area zone. Okay, so very less contact, and because of that reason tray efficiency falls at very low level. Okay, so this is the reason why dumping should be avoided in all cases. Now this has been this problem arises due to dumping. Now the same problem can be arised by different mechanical problem. For example, if my tray sagged, I mean tray is not level, some part is below, some part is having a depth higher, and some part is having lower depth. In that case what happened? The hydraulic tray pressure drop at that part becomes high, and in that case also dumping will start taking place. So in that case also the same problem arises. Similarly, if my whole tray is not level, I mean the ideally tray should be horizontal, and if my whole tray is not level, in that case also vapor will start preferentially flowing in that direction where hydraulic level is less, and liquid will start flowing from that direction where liquid level on the tray is high, and in that case also channeling will take place. I mean vapor is flowing from other part of the column, and liquid is flowing from other part, no intimate contact, so tray efficiency goes very small. So we can see that either by dumping or by mechanical problem, tray efficiency may go very low. Similarly, mechanical problem may lead to flooding also. For example, ideally what happen, ideally the wear height, I mean top edge of the wear height should always be above the bottom edge of the downcomer. Okay, for example, you may see this here, top edge of the wear is above the bottom edge of the downcomer. This should be the ideal condition. Now suppose what happens, top edge of the downcomer, top edge of the wear remains below the bottom edge of the downcomer. In that case there won't be any liquid seal. I mean if this bottom edge of the downcomer remains at very high level, so even the crest height will not be able to seal this liquid, seal this downcomer clearance. Then what happen, vapor will start flowing through this downcomer area, and it will restrict the liquid which is going inside the downcomer, and because of that reason what happened, the liquid will back up on this tray. Now if sufficient vapor is flowing through this tray spacing also, then liquid will not dump, rather what will happen, liquid will back up all the tray, and this may lead to flooding. And if vapor is only all of the vapor is going through this downcomer, then it may lead to dumping. Okay, now similarly, if suppose I am providing very less downcomer clearance, okay, what happen in that case? In that case, if downcomer clearance goes very small, in that case the liquid which is exiting from this downcomer, the velocity of that liquid goes very high, and because of that exit loss increases very high. Now when exit loss increases very high, then we have already seen in last part that it may lead to high liquid level inside the downcomer, and because of that reason, if downcomer clearance remain very small, in that case it may lead to downcomer backup flooding. So because of that reason, the bottom edge of the downcomer should be below this top edge of this top height of the wear, but it should not be at very low level. So there will be only slight difference between this top edge of the wear and bottom edge of the downcomer. Okay, so we have seen that that flooding may be because of hydrodynamics problem, and flooding and dumping may also be take place because of mechanical problem. And because of that reason, whenever any column open for inspection, then usually process engineer check all these problems in tray, that whether my tray is level or not, whether there is a downcomer clearance is perfect downcomer clearance is not, or where there is a downcomer seal loss. All those things usually check. So anyway, let us revert back to our main topic, that is dumping, and we have discussed about one part, that is why dumping reduces tray efficiency at very low level. And then let us discuss the second point, that why this curve is like this. Why when liquid flow rate increases, chances of dumping goes low, whereas when in weeping, when liquid flow rate goes high, then chances of weeping goes high. So dumping is usually increased when liquid flow rate decreases. Why? The reason is weeping increases at high liquid flow rate. Why? Because it leads to high crest height. when liquid flow rate goes high, then it leads to high crest height, and high crest height, what it does, it basically increases hydraulic tray pressure drop. Okay. So because of that reason, chances of weeping goes high. But in case of dumping, there is none of the liquid flowing over the weir height. So even if your liquid flow rate going to increase, there is no hydraulic tray pressure drop increases. Okay. So what happens when liquid flow rate decreases? That it provides sufficient residence time for dumping. So because of that reason, when liquid flow rate increases, then chances of dumping will be less. Okay. Now similarly, or of course, if liquid flow rate increases, in that case there will be chances that some of the liquid will start flowing over the downcomer. So rate of dumping decreases when liquid flow rate increases. Now other part is very simple, that when fractional hole area increases, then also tendency of damping increases, because when fractional hole area increases, in that case vapor flow rate through the holes decreases, and which may lead to low dry tray pressure drop. Similarly, when weir height increases, then it may lead to high hydraulic tray pressure drop, which may lead to high dumping. Okay. So we have now discussed about dumping, and we have also discussed about what are the mechanical problem of tray which may lead to flooding and dumping. Now let us try to discuss about one more concept, and that is called turn-down ratio. Now see, if you see this diagram, now in this diagram you may see that there is a range of vapor flow rate and liquid flow rate in which we can operate our column efficiently. I mean, we can operate for this particular liquid flow rate, we can operate from this vapor flow rate to this vapor flow rate effectively. So this range of operation provides flexibility of operation, because whenever we operate any column, we do not operate at a fixed throughput or a fixed feed flow rate. So basically we may change our feed flow rate, we may reduce or increase the feed flow rate. So there should be a flexibility of this, and that is required. Now, so flexibility may be seen by this diagram, or flexibility is also given numerically, and that is called turn-down ratio. So turn-down ratio is basically expressed basically provide the flexibility of any tray, and it is defined as the ratio of design vapor throughput to the minimum operable throughput. So if my turn-down ratio is very high, in that case we may operate at very low feed flow rate or at very low throughput, and we may also increase our throughput without any problem of flooding and weeping. Similarly, in Cedar and Henley, it is defined as the ratio of vapor flow rate at flooding to the minimum vapor flow rate, and it is defined as turn-down ratio. So in Cedar and Henley, it is written that for bubble cap tray, what we find that the turn-down ratio remains high. It is 5. For wall tray, it is 4, and for sieve tray, it is only 2. So there is a very less flexibility of vapor flow rate in sieve tray. Okay, so we have a flexibility of operation. I mean, we can operate our column at low throughput also without any operational instabilities if my turn-down ratio is high. But even in that case, on what throughput we should operate for maximum separation? So we are to answer this question, let us discuss about mass transfer. I mean, we are now going to discuss about tray efficiency, that when tray efficiency will be high and when tray efficiency will be low. I mean, at what throughput we should operate for high efficiency, because there is a range of operation which we can operate satisfactorily, but we are now interested in the optimum liquid and vapor flow rate in which my efficiency goes high. So efficiency is basically is a concept of mass transfer. So we are now in the realm of mass transfer, and we are going to figure out the condition in which efficiency goes high. So usually if any tray is ideal, then what happens? The vapor and liquid which is exiting from this tray will remain in equilibrium, and the tray will be 100% efficient. But this is an ideal condition. In reality, the vapor and liquid which is exiting the tray is not will not remain in equilibrium. So for getting the tray efficiency, we need to know that the amount of mass transfer which has been taken place on the tray, because if mass transfer goes high, then chances of equilibrium achievement of equilibrium goes high. So the mass transfer basically depend on the rate of mass transfer and the residence time for mass transfer. So for tray efficiency to be high, residence time should be high, because when residence time will be high, then it permits diffusion of different component between the two phases, and because of that the mass transfer goes high. So we have to figure out when the residence time will be high. Now residence time usually remains high when liquid pool on the tray become high. Why? Because when liquid pool on the tray become high, then what happens? The vapor which has to cross through this liquid pool remains relatively at longer time inside the liquid. So the time of contact becomes high. Similarly, for mass transfer to be high, interfacial surface area required will also be high, because usually mass transfer rate depends on mass transfer coefficient times interfacial surface area times the concentration gradient. Okay, so if interfacial surface area between phases become high, then mass transfer will be high and tray efficiency will be high. Now when this interfacial surface area will be high, generally when vapor flow rate through this liquid pool is remain low, then what happens? Then vapor passes through this liquid as gas bubble, and the size of bubbles will be large when vapor flow rate is less. So when bubble size is large, then it means that interfacial surface area per unit of volume goes small. And because of that reason, when we increase our vapor flow rate, then what happened? What happened? That it does two things. One thing is that the bubble size reduces. I mean, bubble is passing through this liquid pool at very high flow rate, so the chances of enlargement of bubble remain less. So bubble diameter remain less, so surface area per unit volume goes high. And it also, what it does, it also provide turbulence inside the liquid. So because of this turbulence and because of a small diameter bubble, vapor usually disperse inside the liquid very thoroughly. So because of that reason, high vapor flow rate providing two things: high interfacial surface area and also high intensity of turbulence. Now high intensity of turbulence also increases mass transfer, because it increases mass transfer coefficient. So based on this understanding, what we understand that for tray efficiency to be high, we need residence time high, and also interfacial surface area required high, and high intensity of turbulence is required. So for high efficiency, what we need high deep pool of liquid, and also high gas velocity is required. So based on this understanding, what we understand that if I operate my column at high flow rate, I mean high liquid flow rate as well as at high vapor flow rate, then my tray efficiency will go high. Okay. So because of that reason, usually there is a range of satisfactory operation, but design point or the optimum operating point usually remain at the maximum possible liquid flow rate and maximum possible vapor flow rate. So we may reduce our throughput based on requirement, but ideally if I operate my column at the maximum possible flow rate and the maximum possible liquid and vapor flow rate, then my tray efficiency also goes high and my capacity also goes high. So we are going to operate at higher capacity and also getting higher efficiency. And because of that reason, we might have seen this turn down ratio concept, where in some cases it is defined as the ratio of design vapor throughput to the minimum operable throughput, whereas in other cases it is defined as the ratio of vapor flow rate at flooding to the minimum vapor flow rate at turn down ratio. It defined as turn down ratio. So why it is so? Because usually the design vapor throughput usually will be comparable to the ratio of will be comparable to the vapor flow rate at flooding. So we usually design our column such that my vapor flow rate will be more or less around 90% of the flooding flow rate. Okay, so we are going to stop this discussion right now. I have given all these concepts from different books. I have just compiled all this information from the normal Liverman books. I have also taken some concept from Treble and some concept from Searer and Henley. I have also used Henry Kister distillation book, and some of the diagram I have taken from different websites on the by searching through Google. So I'm trying to, I want to give credit to all those sources for this lecture. So we are going to stop this lecture right now here, and in the next part we will discuss about the factors of we are going to discuss about the effect of design parameters on flooding and weeping. So thank you.